Hello, welcome to another impromptu PlayBASIC live video. Someone posted something about a competition, and in the competition you have very strict rules. You have to make the game. There's running at a resolution of 320 by 200 pixels, so kind of a classic 8-bit resolution. But the main one is that it actually requires, or they require, that you only use 16 colours. And of course, if you're making images in a modern art packages, that's kind of pretty difficult. Classic art packages from back in the 8-bit generation, 16-bit generation tended to be, well, they were all palette mapped. So you picked the number of colours the image would have, and you could just set each colour index to a particular colour, depending on the hardware you were running on. I'm thinking mostly of the Amiga here. It's one I was sort of most familiar with. So if we have a 16 colour screen, we can make that with a palette mapping. And we actually have a library in PB that does palette mapping. Just try and look it up. It's down the bottom under libraries, palette mapping. Got a few. It's pretty basic stuff, really. So I figure if we have a palette and we use our palette map strip 8-bit and just use the bottom 4 bits, then we can actually make a 16 colour screen pretty easily. It's a bit cumbersome because images in PlayBASIC are actually a minimum of 16-bit, and they are RGB images, they're not palette mapped. So what you would have to do is convert that RGB image into so the colours are converted into colour indexes, and then so when it's drawn, cumbersome, but it works just the same. There's some remapping support in here as well. Index RGB, palette map dot. Okay, so we'll have a bit of a look at this example just for the sake of refreshing our memories. This one we can load from the help directly because it's got the link there. We'll just try and run it. I don't know what this does, by the way. Alright, we've got a palette animation. So the picture is actually drawn, and then the colour or the changes you see are just the palette being manipulated. Because we're actually using a system that doesn't have palette mapping in it, the Windows is basically an RGB sort of multi-byte colour system rather than a palette system. We have to render the palette mapped image out into a coloured image to get to see the screen, but the effect is pretty much what we want. I think what we'll do is we'll grab, actually we'll just grab those few lines there, that'll do us. And we'll start a new project. Let's just start one from scratch actually. If you're not sure how to do that, close the help there. Up to file, up to new, blank project. We'll paste our code in. So we're making an array that's going to hold our palette, our color values. We're telling the library to use this array as its palette. So when we draw these images out, it's going to use these colours as our mapping. If you run this, not much will happen, as you would expect. Sync wait key. I think in the other example it uses a bank, from what I just picked up in the bottom there. Yeah, so it makes allocates a bank the size of the screen fills that in with color values, it computes color indexes, I should say, and just sets them up like that. This is drawing that chunk of memory onto the screen as a list of palette map strips, 8-bit strips. So each byte is used as one color. That would mean that the palette possible range is 0 to 255. They're not signed. But what we could do, this is kind of a bit left of field as well, we could make our screen, we could create effects image as an extended version of this. This is one of those kind of ones that's a bit hidden, I guess. What's our width going to be? We'll set it, no, actually. Have a constant screen width 320, constant screen height 200. Just fill those in here, so we're creating a surface that's the same size. If we go to the help on this command, you'll notice it has one extra parameter. The normal create effects image command has your image index, your width, your height of the surface, but no depth. That's because the PlayBASIC graphics library, once you've chosen a screen at the start of the program, every image you create from then on is created in a compatible format for that screen. And different systems actually use different color formats. It's a bit of a problem. It's actually a big pain, to be brutally honest. But what we'll do here is we'll make this buffer be 16-bit. Now, regardless of what the screen format is, this image will be created in 16-bit. We better get an indexer here. So we'll go get free image. And we might start saving this project as something. So we'll save this as, I don't know. Okay. I like to give things dates and when I've done them up front. So I'm just making a folder to save my project into. And this is going to be, retro. Retro 8-bit computer. So I've created a folder. I need to go into the folder now to save my project. I'll give my project a name. Just call it the same thing. So when I go to reload this thing, retro 8-bit computer. When I go to reload it, it'll appear in this list of here. It won't at the moment because I'm still actively working on it. If I closed the project, went back to reopen, we'd have retro computer there. It's just easier. And even the one that we loaded from the help is still in there too. So where's that one gone? Palette mapped 8-bit strip. Alright, so we've got a palette mapped, an image we're going to use for our palette mapping. It's just a normal PB image. So PlayBASIC has done all the allocation, preparing of that image. We're going to use its pixels not by storing RGBs in them. We're going to just store the indexes of the colours in our palette. So if we define our palette, I'm not going to run through and define heaps of colours, but let's say colour 0 is going to be the blue background colour. Colour 1 is going to be white. and all the other colours will just be black. So if I try and write to them, they'll do weird things. I don't have to set that before there. I can set that after the set palette, by the way. So if we run it, it does nothing. Don't get excited. Nothing. There's nothing to see there. Now, if I want to draw to this surface and use a traditional sort of like PlayBASIC built-in feature, if I draw a line, so if we go render to image, screen, image, so rendering is currently only being drawn to this image we've just created. If I draw a line, I don't know, 100, 100, 200, 200. Redirect rendering back to the screen. If I draw the image, nothing different will be seen. It'll look just like every other. We haven't actually done anything with it yet. We need to draw this out as a palette mapped image. And what have we done? Oh, that's the one, screen image. So we're creating this image of 16-bit and then drawing it back to here. Seems the dogs are going to play up. Yeah, good dog. Good dog. Just pause that there. Alright, here we are back again. Dog was out there playing up like a crazy person. Crazy dog. So, where were we? We were putting together an example that uses palette mapping that creates a kind of a classic 8-bit display that's 320 pixels by 200 pixels. So far we've got something that will render, just appear to render a line on the screen. That's interesting. I'm going to start doing that, is it? I don't know why it does this. Okay. So what we've got here is we're just drawing a normal image, drawing a line to it. That line will be drawn in the current ink color, which will be an RGB color. By default, I think it's white. Pretty sure it is white. So what we will need to do here is we'll make a function. We'll say render, computer screen or something. Oh. Palette mapped screen. We'll give it our screen image, which is going to be this image up here that we've created explicitly with a 16-bit buffer. We'll give it a position where we want the top left-hand corner to be. We're going to make a few assumptions in this function because we're going to have low-level access to the image. So we want to, inside this function, we need to do a couple of things. First we'll grab, what's the old surface? What surface or image are we rendering to? So at the end of here, we go render to image, we restore that. So if we call the function and the current image has been changed, then the current output is not the screen. When we set this to render to the screen, the user won't be surprised about the surface or the render output changing, if you understand what I mean. Alright, so we want really just a while loop. We want to go from the bottom of this image to get image height, screen image, -1. Because the surface here is an effects image, we want to lock this surface after we render to it, or lock buffer, of course, unlock buffer. Some of the terminology, like I'm referring to buffers as surfaces and surfaces as buffers. It really comes from that sort of how things actually work internally. It's a bit frustrating, but they mean the same thing. A surface is the current thing you're drawing onto, whether it's the screen or an image or even a captured situation. So we want to lock the buffer here. We want to get image pointer. We want to get image pointer, screen image, get a pointer to the, this is the location in memory of the top left hand pixel of the image. We might do something at first, when even before we do this, we'll get image depth. We explicitly, this is only going to work if the image is 16-bit, so we want to check if it's 16-bit up front. Just have a quick save there. Alright, so we're checking if the image is 16-bit. If it is, we continue on. We remember the current surface. We change the current output surface to the screen. That's our function says we're doing. We're rendering a palette mapped image to the screen. I've got the pointer to the top left hand corner. It's probably called pitch. This is the number of bytes that the image that actually has across each row. So an image that's 100 pixels wide, whoop, bang something else, in 16-bit will be at least 200 bytes wide. It might be wider, and that's to do with the graphics library likes to align images in memory on boundaries of 32-bit. And that's because CPUs prefer that. So, same as GPUs, by the way, when your GPU creates an image, it will often create an image bigger than what you expect. And it's a bit of a lottery as to how and when this occurs. Alright, so we've got a pointer to our image, the top left hand corner, with the number of pixels across the row from each one, and that lets us create all we need actually. We've got a function up here in our palette map library. Draw palette map strip 16. Okay, so it requires the pixel coordinates of the output, the address to read from in memory, and the length, the number of pixels wide it should be. And the mask, I think, is actually to limit the number of colours. So we'll use that here, so we only get 16 colours. I just use my lazy cut and paste. I do that all the time, probably shouldn't do that all the time. Okay, so we're going to draw this across here, and so this is the image pointer, and the length is going to be the width of the image. Now, one thing we are assuming here, we are assuming that our screen is the same size or smaller than our image. If it isn't, we're actually at risk of this program crashing, because we are accessing pixels on a low level. Alright, we've got a width there. We only want the bottom 15 bit, the bottom 4 bits of the palette to be rendered. So we set our mask to F. The vertical position should be Y loop, and this should be just 0. Although we can just set that to X position up here, and we'll just set Y position here. Now that should actually work. Get rid of the rendered display here. Draw a palette mapped version of that screen. And just draw it to 0, 0 on our output screen. Give it a save. Hit F5. Oh geez, why is it doing that? And we get nothing. Cool. Alright, what's wrong with this? Since we're rendering to a new surface, we might just make sure that we grab a pixel from it, this RGB. The reason for this is that the graphics libraries, some commands have to set up the current surface all the time, and point is one of those commands, and it doesn't destroy the surface, it just reads from it. As other commands actually require this. Oh well, there's an obvious reason why that's not working. Image pointer here has to be output. We draw one strip, then we move down the image. Move down to the next strip and draw that. That's more like it, isn't it? Now we do have our blue screen. We have our line. Our line is not white though. If you remember back to the initial part of the conversation, that's because when we draw a line, we actually have to draw it as a color index, and we can do that if I use the line function. And normally with line C you would supply with an RGB color. Now we need RGB to index. Let's check that is the command or the function. Yes, RGB to index. So it takes our 32-bit formatted RGB color and converts that to an index. No, sorry, we need index to RGB. So I want to draw color 1, which is our white color, onto this surface. And once we draw it, we want to render that surface, which is a palette we're using as a palette map surface, to the screen as an RGB surface. I doubt you're following that, but if you are, well done. And there we go, it actually does work. Amazing. So if we do something like, we'll set up a little loop here, bit of a do loop, nothing too fancy, but something that's a little bit more interesting. Put an end statement at the end. So if we hit the space key, the program will just end. When I do a CLS, I think we might need to initialize some more colors there to make this a bit more interesting. So we'll set up the first 16 colors for loop equals 0 to 15. Palette loop equals random RGB. Just give it a random color, and then I'll reset these first two colors so they're always blue and white. So we do have something to look at. If I just draw a line randomly to the buffer, random screen width, let's do it like this. X1, X2, and Y1 equals Y2. So the line will sort of connect to the previous line all the way through. We're just going to get a spaghetti looking material on screen, or mess on screen really. So we'll compute the end coordinate. At the start we need to really compute initial starting XY coordinate. So when we first draw the line, it will be from X1, oh god, X1, Y1, X2, Y2. Then it sets the new X1 as the old end point and then just continues on. Give it a save, give it a run, so there we go. Right, we're getting a bit of a mess on screen. Pretty cool. Hit space, gets us out of that. If we randomize this thing here, we'll actually be able to pick, if it's just between 1 to 15, we'll be using these colours from our palette. So we'll go random 15. Yeah, we should have stopped doing that. So that's the screen as it in our palette map form. If I render that image out to the screen with just draw image, it won't look like that. Draw image, we'll draw it beside that. We'll draw it at 400, 0, and not transparent. So we'll see the image isn't actually RGBs at all, it's palette indexes. They'll all be very dark blues because that's how the colours are stored in the pixel. Wow, there you go. What we probably could do actually here is we could have something along the lines of, we could have a second surface that is maybe 32-bit. We could just call this palette screen image. We'll just go, FX screen or something like that equals new FX image screen width, whoops, screen height. When we're drawing, we need to render to the palette screen, and when we render this palette screen here, we could do something a bit more. Render the effect screen. So you could render one image onto the other. Render image to effect screen. Hope that's the right variable. Effect screen, looks like it is. This is the palette screen image. Render to screen. Oh, there we go. Now, what we could do here is we could just use the draw image to render our effect screen onto the main screen. We want to draw that. Oh, sorry. We want to draw the effect screen and the palette screen. Palette screen image. I think I made a blunder in there somewhere. Let's just try it out. So there we go. Oh, okay, we're rendering to screen here. It actually needs the target. So, source, palette, image. Destination, image, equals 0. It's just one way around it. So they have the image here, that renders the destination image, and we'll be able to set the effects screen here as our target. So we don't actually need that here. I know I'm sort of rumbling through this pretty quickly. Oh, there we go. So check for the source palette image. Probably source paletted image, shouldn't it? Shouldn't it be? Yeah, it's always handy to try and make your variables at least somewhat represent what they're actually referring to. It doesn't always work that well, I guess. You know, sometimes it's just you think of one idea for a variable name and later on you go, what the hell is that? Oh, I think we've got a bit of a destination image there is render to screen, effects screen. Oh no, sorry. That's the XY coordinate, that's the output screen there, so was just trying to render that to screen 0. Alright, so on this side here we've got our palette mapped image or version of it, and we've got this one here, we've got our RGB render of that, and that's useful because we can do something like use draw rotated image. We'll scale it up. Just say angle 0, 2, handle 0, 0, and that should double it in size. If this thing will ever do that. There we go. So it's more like a retro computer looking screen with a nice chunky low resolution. The two things there are flashing over each other because they're trying to render to the same space. There you go. We could do other things. We could use like a circle function here. You can just draw images as well, as long as you convert them to palette mapped. Get our mouse position, mouse Y, 32 pixels. We will fill it. We'll make sure we provide it with a. We use color 8. Current color variable, and if the mouse button is down, we can make this kind of a Boolean expression, but we'll just do it like this. Plus equals, we'll just go this plus 1, we'll end it with that. So we'll range between 0 to 15 and then roll over. little bit of logic there to stop the rollover possibility. So when the mouse button is not down, I'm just setting this to false. So we should get a circle at our mouse position, or roughly. Just happens to be in that blue background colour. The mouse won't relate to the screen because the screen's being stretched twice the size of its actual size. There's different colours. There you go, wonderful world of palette mapping. If you scroll the colours through, it looks like it's all classic, colour cycling from back in the day. Okay, that's about it for this little session. I was just testing out a mic actually. That's why I made this video. So hopefully you get something out of that, and maybe you can come up with some crazy ideas and how you can use this stuff. Thanks for watching, and I'll catch you next time. Bye.